should be on full screen mode.
Thanks for the introduction. Thank you for being here. So the paper I'm presenting here is based on the part of my ongoing PhD thesis, and well, as usual, it's still work in progress, so any comments on this are really welcome. The Woods-Fildes theory that's in this title is also known as the theory of anti-metabolites, which are a kind of drugs, category of drugs that act by competing with or replacing an essential metabolite of the cell metabolism. These drugs are nowadays used in several fields, several medical fields such as pharmacology, metallurgy, or infectiology. So, my title, Putting Biochemistry to Work, comes from the fact that the anti-metabolite drugs stem from biochemical research, and to the eyes of many researchers, they embody the idea that fundamental research in biochemistry would lead to great advances in drug discovery. But this title also refers to the fact that the anti-metabolites went back into biochemistry and were used as tools of research to gain more knowledge on cell metabolism in general. In this paper, I will try to illustrate the double status of those compounds by taking the example of antagonists of folic acid. At first, I will briefly present the origin of the Woods-Fildes theory, anti-metabolites. So, starting in the 1920s, the field of bacterial biochemistry was really expanding, and the group of Thibaut Serviant-Fine, the bacteriologist in London, were specialized in studies in bacterial nutrition that aimed at discovering essential metabolites, or essential growth factors, as they were also called generally, of different bacterial species, in the same way that experimental animal studies were trying to were carried out to find out new vitamins that were really the height of medicine at the moment. So the origin of anti-metabolites also came from another direction. At the end of the 1930s, the introduction of the sulfa drugs into medicine really changed the face of the treatment of infectious disease. And it raised considerable hopes about chemotherapy as a new way to discover potential enhance the effects of drugs. Hence, the problem, the mode of action of sulphonamides quickly became a very important scientific matter. Woods-Fildes took up this problem, and as one of his colleagues told him that his experience in bacterial biochemistry might help to solve the case. He put the young biochemist of his team on the task, Donald D. Wood, who published his results a few months later in 1940. And in this article, Wood argued that he had identified a new essential metabolite, which is para-aminobenzoic acid, and that the mode of action of sulfa drugs was that they were competing with para-aminobenzoic acid because they are structurally related with this compound, and since they competed with this compound, it was deprived of cell metabolism and hence growth of the bacteria was stopped. So this was soon accepted as the most credible hypothesis on the mode of action of sulphonamides, and a few months later, his boss Woods-Fildes published another article in The Lancet, which is entitled Rational Approach to Research in Chemotherapy. And in this article, Woods-Fildes really generalized the discovery of Wood, and he proposed that this competition between two structurally related drugs could in fact be used as a convenient way to discover new drugs. So it would just require to start from the known essential metabolites and then to chemically modify it to try to synthesize anti-metabolites. When this general theory of anti-metabolites was elaborated around 1940, and was later referred to as the Woods-Fildes why this theory was in my title. It was really explicitly thought of as a rational way of discovering new drugs. And it was quickly taken up by researchers interested in pharmaceutical outcomes, be it in the academia or in the pharmaceutical industry. A few outstanding drugs really came out of this broad program, such as methotrexate, which is still used in cancer, against cancer, pyrimethamine, which was used against malaria, and pyrinol, which is still used in the treatment of gout. But researchers also had to face many disillusions and disappointments, since a lot of the newly synthesized anti-metabolites were really not specific and they proved to be too toxic to be used in medicine. Thus, in fact, I think that the early history of anti-metabolites offers a really practical way to tackle the whole discourse of rationality in pharmaceutical research, and tackle it from a historical perspective, and to see how the impact of the discourse of rationality in pharmaceutical research and how it kind of reacted in front of failures such as huge toxicity and lack of specificity. So, while this idea of developing new drugs based on this anti-metabolites principle spread, hundreds of new chemicals were synthesized and their properties were also exploited in biological research as tools. In fact, they could be used in nutrition to simulate deficiency diseases. If you wanted to simulate deficiency disease, you take an anti-metabolite of a given vitamin, and it will create disease associated with the lack of this vitamin. But they were also used in biochemistry, as Dwayne Woolley puts it, who is a biochemist at the Rockefeller Institute in New York. And so they were used to discover new metabolites, to attribute functions to previously recognized metabolites or trace metabolic pathways. Now I'll go to my examples of anti-bacterials to try to make it a bit clearer. Anti-bacterials are anti-metabolites of folic acid, which is vitamin B9. In the 1930s, which is a period sometimes described as the golden age of nutrition, George Miner, George Whipple, and William Murphy were awarded the Nobel Prize for their work on liver extracts to cure pernicious anemia, and created a lot of research to try to find which vitamins were in those liver extracts that gave us healing powers in blood diseases. But beyond science, the commercial incentives of vitamins were really extremely important as well, because the period of vitamania, the prima apple, and vitamins were really at the center of the economic growth of the pharmaceutical industry at that time. So it was really hot topic, and a lot of means of research were attributed to vitamin research in the pharmaceutical industry. This is the context when the chemists of the leader laboratories, which is the pharmaceutical branch of American Scientific Corporation, published in 1946 in Science this article about the structure of the alkali factor, which is folic acid, in fact. And you can see by the number of citations of this article, which is quite unusual for the time, 16, that it gives an idea of the means that were used in vitamin research in the pharmaceutical industry. And this is when the story rejoins the thread of anti-metabolites, because once the chemists of leader laboratories had the structure of folic acid, they could use the theory to try to synthesize antifolates, anti-metabolites, and folic acid. And this was a challenging venture for a lot of physicians interested in blood diseases, and particularly it really interested Sidney Farber, who was a pediatrician at the Boston Children's Hospital and who studied kidneys in children, So he started a collaboration with the chemists at the leader labs, and he wanted to try anti-metabolites of folic acid to try to cure leukemias. And well, he published this article in 1948, the use of immunotherapy in leukemias, which was really perceived as a breakthrough because it was the first time that remission were produced in acute leukemias in children. A few months later, he published another article with a more efficient compound, which is methotrexate, and is still used today. So it was a breakthrough in medicine, but we have to remember that the successes were modest. The remissions were temporary. The children eventually died a few months later because the drugs, the cancer, the tumors quickly became resistant after a few months. And in the meantime, so that was the medical world, and in the meantime, another line of research was done with anti-metabolites of folic acid in biology. Since the end of the 1930s, the biochemists there was a growing interest on the metabolism of nucleic acids, and this growing interest grows much faster after the work of Oswald Avery and monocroppal transforming factor. Around 1950, a body of evidence was mounting, pointing to the recognition of folic acid as a central node in the metabolism of purines and pyrimidines, which are the components of nucleic acids. And the first proofs on this matter and the fact that folic acid is involved in the metabolism of nucleic acids were brought about by anti-metabolites. So very quickly, this biochemical point, in fact, because investigation on sulfa drugs that led the researchers to the idea that there was a relationship between pyrimidine, benzoic acid, folic acid, and purines. And then the synthesis of folic acid was shown to reverse the action of analogs of purines and pyrimidines. And on the opposite side, the effect of folic acid analogs, such as methotrexate, were stopped by nucleic acid components. So this was how the whole link between folic acid and nucleic acid was established. So, as the example of folic acid shows, the use of anti-metabolites as biochemical tools really indicated the pathways of synthesis of several metabolites and gave clues toward finding the intermediary compounds that were involved in those pathways. This does not mean that the anti-metabolites were the sole option available to biochemists. There was also the use of Newton's strength that carried metabolic specificities to trace metabolic pathways, and also the use of radioisotopes, which were really widespread and radioisotopes that proved really efficient to trace the transformation of compounds throughout the cell metabolism. It was the combined use of these methods, Newton's strengths, anti-metabolites, and radioisotopes, that was promoted by biochemists in order to understand the metabolic pathways of the cell. Am I on time? So, the anti-metabolites really incorporate this idea of rational way of drug discovery. And some of the chemicals that were synthesized that emerged from this adventure really coexisted between the world of the physicians and the world of the biochemists and the pharmacologists. So this is not, this picture is obviously not limited to anti-metabolites. Many other substances were simultaneously used as drugs and research tools in biology. But nevertheless, I believe that the history of anti-metabolites can offer an interesting and specific perspective on this kind of double status between drugs and tools. and this kind of double existence between bench and bedside, as John Mallory puts it in her book. And thus, I believe that the history of anti-metabolites can provide a practical way, a useful way to link the history of drugs and pharmacology and the history of biology that had sometimes been a bit separated on the side.
Thank you. I'm now prepared to entertain a question or two for specific in your mind.
So, one very specific question, just out of ignorance, and maybe one more general one to sort of what they would need to do to create drugs that would not have this toxicity.
Yeah, this is a great question, and this will be about my thesis, but I didn't want to put it there here to be like inside. But really, anti-metabolites and their toxicity and lack of specificity really showed researchers that the metabolisms of bacteria in humans were more closely related than we thought. Well, it is the conclusions of the biochemists working on those products, but I'm not sure whether it was the anti-metabolites that helped to make the link between those metabolism and unify different forms of life, bacteria and humans. I can't say that yet. Maybe this maybe the comparison between bacteria and humans came from another one. So I'm not in firm ground.
Yeah, no,
I'll be saying that.
And my other kind of, as I said, this is a bit unfair. In some ways, it's a suggestion, is to say that in the history of sort of physics and also in the history of biology, there is some writing about creating your own investigative tools, right? And this is in some ways specific to the history of physics creating machines and tinkering, and the history of biology breeding and domesticity. And what I'm fascinated by is the idea here that there might be something specific in chemistry or pharmacology where creating your own tools is a somewhat different process, right? We know that scientists do this quite often, create their own tools, investigate their own tools, but I would be very fascinated as this project goes on, whether you can find ways in which the chemist's creation of their own tools is different from physicists or
Okay.
as I said, totally unfair question, but I think it's really an interesting possibility.
Yeah, very interesting question as well. And well, the idea of tools of research is, extremely classic. It's the anti-metabolites are not the only tools in chemistry, of course, but so I'm not. I don't say that they were tools in a very specific way compared to other tools, compared to radioisotopes, compared to other reagents or enzymes. So I'm not sure if I'll be able to see a distinction between chemists' creation of tools and other disciplines. Yeah, it might be interesting.
Thank you. Anything else? Yes.
You mentioned the phenomenon of resistance. What were the reactions of the chemists faced with this problem? Did they regret it? And did they try to create new compounds which would not eventuate the organism would not be resistant? What happened?
In cancer, you mean?
Yes, for instance,
Yeah.
for anti-bacterial
Yeah.
effects after anti-bacterial.
They were concerned by the resistance in the clinic. They faced the problem, but I'm not sure whether cancer researchers have the solution to this problem, because in fact they
Did they understand what happened? Did they imagine the explanation?
from the Darwinian perspective on cancer cells?
What was the origin of resistance? How did they
It was, I think it was a general idea that tumors become resistant in the same way as bacteria become resistant to antibiotics, but very little was known on mechanisms of resistance in the cells. So they did try new drugs, and they hoped that they wouldn't induce resistance, tumor resistance, but it was chance. I think I don't think the researchers in the 1940s and 1950s